finally, we have to think about the hardware architecture, right? So far, we have talked about the network architectures, but the hardware architecture is certainly going to play a very, very important role in determining what the energy consumption is going to be, right? What's the latency? How long is it going to take to, infer? How long is it going to take to actually train my neural networks? What kind of power consumption, what kind of energy consumption I'm going to have. Energy consumption turns out to be quite important in case of edge applications, IoTs, edge applications. And in fact, for such applications, latency turns out to be also quite important. And also remember that for such applications, for example, edge applications, the sensor data is basically very close, and the sensor data just directly goes into basically the edge devices. Can I effectively process that sensor data to be able to do the right kind of computations? So that turns out to be important. So while we're going to be, we have to talk about the right kind of device and hardware architecture. But before I do that, I felt it's actually important to think about the system as a whole. And we're going to talk about sensors, we're going to talk about network architecture, and the hardware that we can potentially do. So far, we have talked about the network architectures. We have talked about a little bit about the sensors or the input, how the inputs should be, and training of such networks. Now let's see that if we can apply that, and then finally we'll talk about the hardware architecture, but let's try to apply that to a system design. So what would be such a system? In this particular case, we actually looked at a completely vision-based neuromorphic navigation. So the basic idea in this particular case is for a drone to go from point A to point B using only vision sensors. And in this particular case, we have two different types of sensors I'll talk about. So it's a cross-layer design that we need to look at. We're going to go from sensors to algorithms we talked about, and then the hardware architecture. So it requires, we'll see a cross-layer design approach. And the first thing that we have to do, going from point A to point B for the drone, and if we are humans, how would you do that? You first have to figure out what's around you, right? And what objects are moving, what objects are not moving, right? Stationary objects. So we have to do what's called optical flow. We have to estimate the depth of the objects, how far they are, right? Segmentation, and then if there's some moving objects, I'd like to track those objects if I can, and then plan my objective of going from point A to point B. And then I have to obviously take some actions. The motors of the drone has to be activated in some ways to go from point A to point B. So to start with then, the first thing that I have to do is that I have to have some sensors which are going to sense the environment. And that sensing is done using two types of cameras. In this particular case, one is going to be what's called a standard frame-based camera, and the other is a DVS camera, which is a dynamic vision sensor camera. The difference between two cameras are the fact that in the standard frame-based cameras, we're all familiar with, frames are available, but in a DVS camera, which is more neuromorphic, if I may say so, the idea is that when there's a relative motion between the camera and the object, there are spikes that are produced. And those spikes are going to be quite important, and the spike, when spikes are produced, the timing between the spikes is also going to play a role in determining what kind of optical flow that I have. So sequential information turns out to be quite important. So I need to think about, hey, these inputs that I have from my camera should go into a network architecture. So what should be the network architecture like? Should it be a spiking neural network? Should it be an ANN? Should it be an LSTM? Right? Those are the things that we talked about. How would I do the training of such a network? To have my objective of having the optical flow, to have the objective of basically object detection, tracking, and so on. And then finally, these network architectures, whatever I do, has to be finally implemented in a hardware. And what should the hardware be like? Should it be like a standard GPU kind of architecture, which is von Neumann? Or should I really have compute in memory, and we'll go into that a little bit later on, to do better, faster computations. So to that effect, let's start with first the sensors, which is basically frame camera versus the event-based cameras. The frame cameras are the standard cameras that we're all familiar with. Now what one can do for as an example, optical flow, is that I can have a standard analog neural network. By that I mean the standard deep learning network with an encoder-decoder kind of architecture where I have where I can determine the flow. The only problem with these cameras are they can potentially have motion blur and they don't have a high dynamic range. So to that effect, what one can also think about is a event-based camera. As you can see on the screen, there's a dot which is moving around. So when the dot is moving, the DVS output basically is based on the relative motion between the camera and the object. When there's no motion, there's nothing that happens. The output is 0. But when there is a high-speed motion, as you have seen, that in those cases, there's less of motion blur. So with that in mind, now that I have spikes which are going to be generated out of this camera, and the difference and the timing between the spikes is also going to be quite important in terms of figuring out how speed and which way the object is moving, I probably have to use that input information to process for my optical flow. But at the same time, it's also important to understand that maybe I can do a reasonable optical flow with that, but if I do also at the same time have intensity information, which this camera doesn't have, right? Doesn't provide directly the intensity information, is it possible that I actually use the same intensity information to get better flow, right? So to that effect, one can actually think of an architecture. If the inputs are only spikes, then, and the timing between the spikes is also important, I can potentially use, for example, a spiking neural network. Can I use, for example, an ANN? The answer is yes, but it may not be able to capture the timing between the spikes well. Okay? The membrane potential of the spiking neural network, remember we talked about earlier, that can play an important role in determining the past information. So, and the second thing that is also important is that, hey, if I use both cameras, is it possible that I use a hybrid or a combination of ANN and SNN to do the job? By taking the best of both worlds, can I really do better processing? So that's the kind of thing that we need to look at. So to that effect, let's try to now look at the network architecture and try to figure out, hey, what kind of network architecture should I use? Should it be ANN, SNN, LSTM, hybrid, and so on? And let's try to look at, as an example, optical flow, which is required everywhere. So what is an optical flow? The optical flow basically is the fact that I require understanding of the world around me, right? And in general, it turns out that when I see objects, they're three-dimensional vectors, but it goes through my retina and gets, then it becomes really a two-dimensional object. So in other words, if I'm really thinking of a camera, from a 3D motion vector to 2D motion vector is what I'm really interested in when it comes to optical flow. And to that effect, the estimation of a 2D motion field by computing the spatial and the temporal variation in the pixel intensity is optical flow, and that's what I'm going to do. And this is an example of sparse and dense optical flow that I'm showing at the bottom. Now, that's a basis of a lot of the computations that you might be doing for the drones later on. So optical flow is absolutely important. So what's the network architecture for optical flow? So one of the things that we ended up doing in this particular case is we came up with a fully spiking network architecture. So just taking inputs coming from the DVS camera are what one can do is one can actually come up with a fully spiking network architecture. How we actually come up with and train this network architecture, I'm not going to the details of it, but it turns out it's possible to do that. And in this particular case, looking at the data sets that we had, MVSEC and other data set, we actually needed about 13 million parameters to do that and get good what's called the endpoint accuracy. Now, the question then becomes, hey, can I do slightly better using those 13 million parameters maybe, but now, or maybe using a less number of parameters by taking the best of both worlds? Can I really take now the inputs coming from the DVS camera and the standard frame camera, both the inputs, merge them together using a hybrid network, an ANN and an SNN, merge them together, and then do the computations. Again, a still kind of a UNet kind of architecture, but if I do that, it turns out I actually end up getting better results. Why? I'm taking the best of both worlds, right? But if I do an ANN, it doesn't do really as well. And what is very important to understand here is that I do better with 7.5 million parameters. Now, half the parameters, I do much better. Now, we also wanted to see a little bit more and say, hey, how does spiking networks do? And can I really have a very lightweight optical flow architecture? And to that effect, we actually looked at a little bit different architecture, which is called a fire flow net, which is not a UNet architecture, but wanted to see how good or how bad we do using only 60,000 parameters in this particular case. And I'm going to do some comparisons to show how well it does. In fact, interestingly enough, the 60,000 parameters certainly doesn't have the kind of endpoint error that we are expecting out of these larger scale networks, but does reasonably well, for maybe reasonably well for the kind of applications that you're looking at. So to that effect, what we did is we looked at various such SNNs, spiking neural networks for doing optical flow, and compared that with those adaptive flow net or these hybrid architectures that we looked at, the best ones that we could get using an ANN. And wanted to see the number of parameters, which is plotted here, the number of channels, the number of parameters, and the kind of reduction that we can get with this new network architecture. So what is really important to understand here is that we compared the endpoint error with a standard ANN, and then tried to look at these smaller scale spiking networks to see, can I really achieve the same kind of accuracy as the ANN and with much less number of parameters. The reason we are able to do that is because it's a sequential network, meaning thereby it has a membrane potential compared to the standard ANN. And what we found is that we can get the similar kind of accuracy of that ANN when we use about 48x lower number of parameters and about 51x lower number of computations. That's quite a bit of improvement that one can potentially get. And the reason I wanted to underscore this is not because I'm really at the end of it for the best accuracy. I'm still going to go with that large-scale hybrid network that I talked about. But in this particular case, as you can see, that I can get the similar kind of accuracy endpoint error as a standard ANN, but with much less number of parameters. And that's quite a win for a large class of these edge applications. How about segmentation? Again, not going to spend much time on it, but the architecture for segmentation in this particular case that we used, again, both the cameras, the DVS camera and the frame-based cameras. And it turns out that if you take the best of both worlds, there are things that you can't detect in case of, for example, an ANN. I'm showing some examples here with the red dots, which are shown here, the lamppost and so on, which one could not using, for example, a frame-based camera, but could do it with the DVS camera. And a DVS camera also missed something which could be actually gotten through the frame-based camera. So taking the best of both worlds, one can actually get quite a bit of improvement using these hybrid architectures and using both the sensors. And these are some of the results. And again, not going into the details of it, but what it really at the end of it shows is the fact that if I were to use number of parameters and the mean interaction MIOU as a measure of accuracy, turns out that one can achieve that accuracy with lower number of parameters using a hybrid network. Finally, let's also look at object detection and tracking. So for an object detection and tracking, this is actually showing an example of a car moving, which is, and the ground truth of the bounding box of that car is shown here. And event-based one using another framework called YELLOW is shown at the bottom. Now, it turns out that computation-wise, that requires a good amount of computation using such a network. Now, is it possible that I can actually do a much better job of detecting the moving object easily using the spike inputs that are coming in? And the answer is yes. So to that effect, what we did is we actually ended up using a very, one layer of spiking network. And this one layer of spiking network can not only, figure out what the object is, but also at the same time using a clustering algorithm along with it, you can not only figure out what the object is, figure out the bounding box, but at the same time, it can also figure out the speed the object is moving at. Remember, leak was an input that we used, and in this particular case, leak and the threshold combined together can really be used to figure out what speed the objects are moving. If the object is moving at a medium speed, high speed, or a low speed, we can detect that, and based on that, one can now make decisions as to what should be done in our path planning. I wanted to show you a video, and this video basically shows that what I wanted to show here is that there's a ring which is moving, and using the algorithms that we talked about, we figure out, hey, what speed that particular ring is moving, and then based on this DVS sensor which is shown in the front, which is not mounted on the drone, because the drone is actually, this DVS camera is a little heavy for mounting on the drone, but turns out that what one can now do is, based on the speed of the object, the drone figures out what speed the object is moving, and based on that, it can go through the middle of that ring. So this is just an example of the algorithms that we developed and showing that it indeed is quite useful in such applications like edge applications.